So, as I said, my name is Andy Palmer. I work for Seagate in the Enterprise Data Solutions and Cloud product group in the UK. You want to get me going? And I'm going to talk to you about Seagate, but mainly about how the technology that we produce can never get you to carbon neutrality, but it can help you have less of an impact on the environment. And so it's not so much about what we do, it's why we do the things we do that I'm going to talk to you about today. So a couple of years ago, IDC did some market research, and they said that in 2025 we're going to produce 175 zettabytes of data. And in fact, recently they upped that to 221 zettabytes of data, because we've already surpassed 175. So massive amounts of data growth. Now, I'm not going to give my team a bigger quota because of that, because the truth is only about 10% of the data actually gets stored, right? So it's in this, I've got a load of it's in that gap there where we think that there's a big opportunity which is being wasted, right? And the reason why we say that is because our customers now face this dilemma about they've gone to all the cost of producing the data and moving it around, but they won't store it. They have to decide what to delete and what to keep, right? And we think that's a missed opportunity. So what Seagate tries to do is to make data storage as simple and as cost effective and as safe as possible, right? And so that's what we're trying to do here. And I was trying to think of a way of how can I illustrate what 175 zettabytes actually looks like, because it is 175 is not a very big number, but zettabytes is, I think it's 17 groups of 3 zeros. It's a huge number. And I was on the beach, on holiday, and with my feet in the sand. I thought, I wonder if there's more data than there is sand on the Earth right now. And so I figured it out. And so if you type the letter A on a computer, that's about a byte of data. Okay. Then I got one of our interns, and they got the micrometer out, and they measured some grains of sand to figure out what the volume of a grain of sand is. And then we got some geo mapping, and we worked out how much of the Earth's crust is covered in sand, and therefore we can start to make some things, right? And obviously it's an average, right? Sometimes the tide is in, sometimes the tide is out, right? Not all grains of sand are the same, but even if I'm out by about 60%, these are still fantastic numbers, right? So we've worked out that if, bearing in mind that A is 8 bits of data, right? So at the moment, there are 7.5 exabytes of sand on the Earth today, right? Okay, now in 2020, one Earth, there we go. In 2020, the hard drive industry shipped 44,000 exabytes of data storage products, okay? Which is 6,000 Earths worth of sand. And when we get to 221 zettabytes, well, that is 29,000 Earths worth of sand. So we're talking phenomenal scale, okay? And people still say to me, yeah, but can I get $10 off a hard drive? No, you can't. And we are living truly in a data economy, and it's in the data that we see opportunity. It's about combining data sets in new ways, right? And a lot of companies might not think of themselves as being data companies, but the truth is a lot of them are. So a story that I often tell is about Rolls-Royce, who make aircraft engines. But what Rolls-Royce do is they make aircraft engines as a service. So they will ship their engine to an airline, on their airplane, it flies around. And the engine is producing, I think it's like 40 terabytes of data on every transatlantic flight. And what it's doing is transmitting data about its state as it is right now. So if there needs to be some kind of mechanical intervention as it lands, then the engineer from Rolls-Royce can be there with the right tooling, the right spare part, and can meet the aeroplane, get it repaired, get it back up in the air where it can make money again for the airline. So that's all about data being interpreted and being used in meaningful ways. And that, so Rolls-Royce, we would argue, is actually a data-driven company. Now, what drives that massive growth? It's not the 30 billion devices connected to the internet today that become 60 billion by the end of the decade, which is what all the forecasts tell me. What it is it's the insights. We've got this huge amount of data which exists, which is being built and is resides, on Filecoin, it resides on Amazon or wherever it resides. And there's lots of software apps which can combine those data sets in new ways, which provides new insights. Those insights become strategies. The strategies become actions. The action produce results. And the results go back in as new insights. And it's that circularity of data which actually is what's going to drive this huge growth that we were talking about. There we go. Because after all, as I say, the value is the data. Google, are quite open about it. They say that they don't have better algorithms than anybody else. They've just got more data. Okay. So, what are we doing about it? Now, Seagate builds hard drives and SSDs. You may not know that we also build under OEM contract for people like Dell, HP, Lenovo, IBM, Quantum. We are the people that build those boxes that they sell. So Dell MEO4 is a Seagate built product. You also probably won't know that we also have a live cloud service as well, and these are just homes for our hard drives, right? So things I'm going to say from now on are equal for SSDs as well as for hard drives, okay? But we're a big company. We're so 20th century, sometimes it hurts us. We're 40 years old, right? We're the old men in the group right here. And we take 61 elements from the periodic table out the ground, and we source 36 billion parts every year. And we put those together, and to build a hard drive from scratch takes about a year, actually. So, we're a very large manufacturing company, and of course, in that activity, there is a carbon output, without doubt, okay? And our role is to try and be conscious of that and try and find ways of minimizing that. So let's talk about the hard drive, what it actually is. The first one there, this one here, that's the very first hard drive, a massive 4 meg of data, okay? It's the size of about 3 washing machines, and judging by the lift required, it's probably about the same weight as 3 washing machines as well. We no longer provide airplanes with our hard drives, just so we're clear. It's not even a promo activity. Yeah, right. So 4 meg, it cost about $28,000 to rent, and you could only rent it if you were an approved government agency and doing approved government research. Okay, it was invented by it's called Ramac. It was an IBM invention. In the middle there is the inside of a modern hard drive, and I'm going to talk about what those components are, so you understand how difficult they are to manufacture. So this is the platter, right? On the platter is where the actual data is stored. Okay, although it's actually flat and you couldn't see them, there are actually lots of little concentric grooves on that. And if you want to know how big the grooves are, if you take an edge of a piece of paper, in that space there's about 2,000 grooves. Okay, and that's all across that. Into those grooves, we splutter, should we say, or we sprinkle very, very tiny atoms of a metal oxide, and that's why it's called spinning rust, by the way, because it's a metal oxide. And it's the atoms on which actually data is stored. Okay, so we put it in there, and then this thing here is the read-write arm. This thing's called the actuator, and right at the very end there's a little bit of magic called the read-write head, which is where all the IP of Seagate actually resides, okay? And it's how we get that data converted. And what we do, that thing flies over the face of the platter. You can see that there's one of those in between each of the platters in the stack. And it has to fly over near enough so that it can actually have an effect on those little molecules, but it can't touch the platter because that would be a catastrophic failure of the hard drive. Okay. Now, we say it flies because on a cushion of air, but the truth is we don't use air anymore because we found air molecules to be too volatile and too big and also too irregular, so you can't predict it anymore. So we pumped all the air out. We pumped in helium gas because helium is a single atom gas, and it also has less drag as a byproduct and therefore less power to spin it around. And the flight height has to be near enough to affect the molecule but not touch it. And the flight height is actually angstroms, which your fingernail has grown more in the last 8 seconds than the flight height of that thing over the face of the platter. So this is phenomenal engineering that we're doing every day, thousands of times a day. So it flies over, and what it does, it provides an electromagnetic charge to the molecules, and it will give it a positive or negative polarity, positive, negative, 1, 0. 1, 0 is binary code is compute language. So that's how it works. And so those little molecules, that is the physical manifestation of data, right? It is a thing. And if you were to get all those molecules together, currently that reside in the internet, it's about the weight of an orange. So we can safely say it's true. The internet with the World Wide Web weighs the same as an orange. Right. So we can't get much more data onto that platter. Okay, we've got 2 terabytes now. We're launching 3 terabytes, and how we're going to bust through this barrier is over here on the other over here on the side. I'm starting to get a little video going. There we go. So the top illustration is we replace the magnet. And so what happens is, by the way, when we convert one magnet from north to south pole, often we find under quantum mechanics other molecules will also flip on the opposite side of the platter. So what I do is hold them in a much firmer medium, right, which therefore requires too much power to actually flip it. So what we do is we heat it so it becomes a bit more malleable, and therefore we can flip it under less power. And the heat comes from a laser, but the laser dots are too big, so we've got to shine the laser into a near-field transducer, and everyone knows what comes out of near-field transducers? Plasma. The plasma dot is much, much smaller than a laser dot, okay, and that's how we can ram more terabytes into the face of the platter, and we've got a roadmap to 5 terabytes per face of that, and that's how we're going to get to 100 terabytes plus of a disk by the end of this decade. Okay, so massive capacity. But the legacy is, of course, when you've got so much data in such a small space, how the hell are you actually going to use it? And IOPS performance per terabyte drops off. And around about 26, 28 terabytes, it drops off to the point where Facebook say to us, it's too slow. Last year's picture of a cat, I need it now. I don't want the lag. So what are you going to do about it? So what we do, we split the actuator into 2. Because all these read-write arms here, they all swing together at the same time, and only one head can read and one can write at any one time. Whereas if you split the actuator, you double the IOPS performance. Split it again, you can double it again, and so on and so on and so on. So then you get much faster hard drives. We're not saying SSD speeds, and that's not my claim, just fast enough for nearline data storage. Okay? And it's important, especially when we're considering environmental considerations, because as we move up the capacity curve, the cost of power, the cost of infrastructure, everything else goes down. So we want to affect that. You're storing more data in the same space, so you need less rack space, less infrastructure, less power, and so on and so on and so on. So it's a vitally important thing for us to keep on this curve. Now our customers, a lot of our large customers, they will retire their drives after 5 years because that's when the warranty expires. Okay, so they'll just take them and they'll either store them somewhere or they pass them to other third-party companies who shred them, and they shred them to very fine powder, and they put the powder into landfill. Okay, and most years around about 200 million drives just get destroyed, just get thrown away, and we think that's a terrible legacy for the earth. Okay, so we're trying to find ways of stopping that from happening, and the main driver for that, why they shred them and don't just give them back to us, is because they're worried about data security. Right, no matter how you can delete, how often you can delete a drive, there is still a shadow of your data on there somewhere. So what Seagate's been doing in the last couple of years is working very hard on security, and we're about to start selling drives that are only encrypted. Okay, nothing else. The Chinese government and the Russian government have always said to us, you can't sell encrypted drives in our country. I wonder why that is. Now we're saying, okay, well, it's an option that you can turn off, but the standard will always be that the drives arrive at your place encrypted. But it's not just the device encryption that we're talking about. We also talk to lots and lots of our vendors and say to them, you've got to be secure as well, because if you're not secure, we're vulnerable. All right? And there's a story about a US retailer who was hit heavily for I want to say GDPR, a data breach, and the source of the data breach was nothing to do with them or their computers. It was their air conditioning supplier who put plant on the roof of their buildings and had networked those aircon units so that they can control them and monitor them remotely. And a hacker got in through the aircon into the computer system and hacked them and held them to ransom. So you can see how you've got to have your whole supply chain, not just your direct supply chain, but all your supply chain absolutely robust and secure. And we've been working hard for the last couple of years to try and fix this, so that we can say to customers, we can we don't delete the data because it's impossible, but we can encrypt your data, and then you can delete the encryption key, and therefore the data is no use to anybody else anyway. It would take you about 225,000 years to unencrypt it, right? And who's got the time, right? So we're offering that, so therefore we can offer sanitization services, and therefore, and we've piloted this now in Singapore, we can move to buying back drives. So we own the drive for a whole of life cycle. We take them back from you. We can then destroy them ourselves. In fact, we don't destroy them, we recycle them. So drives contain, those 61 elements I mentioned earlier. We can recycle many of those. Or we can use the drives as part of our warranty replacement program. So you can see that drives can be repurposed, reused, recycled. And we've bought back about 1 million drives, and we can recycle about 3/4 of them. So it's a good thing. It's a pilot program right now, but starts to scale from next year. So we can really start to drive down our carbon footprint, if you see what I mean. So that's drives, okay? High capacity, recycle, this the works, right? Now, where do they go? We put them into systems. Lots of our customers buy them from us, and they put them into, you know all the names, right? And a lot of them get built actually by Seagate. But the trouble with systems and traditional architecture, which is RAID, when a drive at 30 terabytes goes wrong, it's going to take you days and days of downtime as it rebuilds. And you've got to have loads of drives spare in the array and so on. So we have moved beyond traditional RAID, and we use erasure coding instead. Okay, and what erasure coding can do, it can isolate single platters on the drive and only offload the data from that single platter and only attempt to rebuild that platter. So it cuts the rebuild times from days down to hours. Okay, and once you've got that perfected, we don't need the compute or the app layer to actually do anything for us. Core Vault will do it all by itself without even the user needing to know. So it's self-healing technology. And this is very good in a distributed architecture where you may not have access to software engineers or hardware engineers nearby. There may be a day's drive away. So this will just go on and self-heal. And if the worst comes to the worst and your platter cannot be recovered, then it will just issue a do not write here statement. And your 20 terabyte drive is now a 19.95 terabyte drive. That's only a 0.25% difference. Okay, when you get to 30 terabytes, 50 terabytes and beyond, that percentage goes down. All right, so self-healing drivers is a very viable thing, and we're selling this as a smart JBOD, so JBOD pricing. So very, very cost effective, very, very good from the point of view of usability. Where's my pointer? Here it is. Now, don't bother to attempt to read this. This is the output from a config tool, that OS Nexus. You might have heard of OS Nexus. They're a file service software. I just used their config tool for the purposes of this illustration. So not only does Core Vault self-heal, it also reduces the amount of cores that you actually need to deploy to manage it. And so on the left there, I have a competitive JBOD with another competitor's compute. And you think about, this is 20 petabytes usable, so 30 petabytes of raw storage, and it's like that because we're using the OS Nexus system as well. And so therefore, it's almost 1,500 drives, and each drive needs a thread mapped to it, so map it to the compute. So therefore, you've got to have 1,500 threads, okay, and each core can handle 2 threads. So therefore, you need to buy microprocessors with at least 720 cores, and you need about 7.6 gigabytes of RAM to manage that as well. You look at Core Vault in hand, which is more than just a JBOD. We've paired it with our own AP blade, which is an AMD EPYC blade server. It doesn't map drives to the compute, it maps LUNs. And so what happens is it maps a nice clean LUN up to the compute, and therefore you don't need as many cores, because the same capacity only needs 384 LUNs. So therefore you only need to buy 256 cores to run that, and half the RAM of the traditional JBOD architecture. So we are reducing cores, and therefore we're reducing all the infrastructure that goes around it as well. The power draw, for example, is much less. The cost, of course, is much less, and it just makes sense this way. And it's, you know, in fact, we've measured it. Of course, this is the best case scenario, right? As you can imagine, for a marketing slide. But we've calculated that actually, the best case scenario is that we've measured that you could lose almost 40% of the infrastructure cost by deploying Core Vault in a Seagate environment. And by the way, that was a Ceph environment. So you can see what I mean. It really does reduce the cost and everything else associated with it. So it's a really good system. And it's important because, you know, companies are taking much more interest in their, not just their own environmental impact, but also their vendors, right? And so Seagate wants to do this, not because it's nice to have, although it is, but because it helps us attract the right investors, it helps us attract better staff, it helps us attract customers who demand it from us. So we've published moonshot goals, you know, we want to go, you know, completely renewable energy at our manufacturing sites. We're halfway there. So 3 out of the 6 are already on there. And carbon neutrality, we don't quite know what that means, but, you know, I think any economic activity will have a carbon footprint, right? So we take it so seriously, and we want to be so transparent that we actually published an ESG annual report. It's our 15th version. It's just come out on the website. Got 10 minutes left. I'm luckily almost there. And it's, you know, this again is just us sort of putting a stake in the ground and saying this is worth doing, not because of the headlines it brings us and the goodwill it brings us, but because it actually makes sound economic sense. For example, those rare earth materials are rare and therefore becoming much more expensive. We can help our supply chain. We can gain more customers and so on. And we're seeing results. You see there the graph. You know, this is the change per terabyte. You can see it as we move to higher and higher capacity drives, the thing drops, and as we go up to 30 terabytes and beyond on the hard drive, those lines will you know, continue going south, which is good news for us, good news for the environment as well. So we're seeing some and measuring our results and seeing some results and publishing them in our annual report. Got 5 minutes left, have I? Yeah. Okay, good. So I'm in the sort of final slide, which is good news. So, you know, when putting this presentation together, I was really trying not to be political, right? Because I don't feel qualified to be. What my point really is that we do these things because it makes really good business sense for us, right? Not because we're nice guys, although we are. It's because it makes good business sense. It impacts our bottom line in a really meaningful way. We're not interested in doing carbon trading. We're not going to move the problem to a different part of the world or anything like that. We're looking to resolve these. And really, my final thought is this, you know, it's only when companies like Seagate get together and start to understand the bottom line impact will we see some meaningful change. It won't be governments taxing us into carbon submission. It won't be activists sticking themselves to roads and annoying everyone. It will be companies getting better results, better outcomes financially that will drive these meaningful changes. You know, technology is upon us, it's there, but it doesn't need to cost us the earth. Thank you.
Do we have any questions for Andrew?
Uh-oh.
Hi. Actually, I have 2 questions. The first one, you mentioned that you buy old hard drives to recycle them.
Yeah.
How much do you buy the hard drives?
How much?
Yeah.
Well, it depends on what you buy, and we don't pay you cash either. You got to buy a new Seagate hard drive in return, right? Okay. So it's a program that's in pilot right now. It's not actually in Europe yet, but it is a contribution to the cost of, more to do with the cost of recycling rather than buying your drive. You know, your result won't be a cheaper drive afterwards. It'll be that the cost of recycling or shredding that drive is covered by us because we want it back.
Yeah, because actually what we do today is like we work with institutions. They have a lot of hard drives.
Yeah.
So we collect this hard drive for them, but like I don't see any interest for us. Like, we don't sell hard drive to them. We just collect these
Yeah.
hard drives. So what do we do with that? Like, if we don't get cash in
What
return.
did you do today?
Today,
Yeah,
we just give to brokers, and that's it.
you just
Send to brokers.
to brokers, right?
Yeah.
Okay, so your service model then would change then, and you probably need to start thinking about offering that the cleansing of the drives, and then therefore you become a refurb reseller.
Okay.
That's what you would do.
Okay. And the other question I have is like, do you see any in the future, like, is resistive RAM something that is coming, or something you are thinking of or you're working on?
I don't know.
You don't know?
No.
Okay.
Sorry.
Thanks.
Thank you. Are there any other questions? Everyone here from David?
There was one over there, wasn't there? I thought. Yeah.
Hold on. Let's get the priorities right.
Thanks, Andy. I'm not sure whether the question really fits in this because, like you mentioned, you're a bit
It's okay.
overqualified
I've
for-
got quite a loose script.
With decentralized data or content creation and pre-storage storage happening on phones, and with the increasing computing capacity of phones, there's a lot of data that gets stored and a lot of data science that takes place within the phone itself before it moves into data centers.
Yeah.
And where the phone capacity is going is known to everybody. Is Seagate, imagining a product where the device doesn't need to have the storage and the computing capabilities because Seagate can offer that? Because I don't see this from Apple or from any of the Android suppliers. Nobody's thinking about the computing capacity of a phone. They're more thinking about it from a content generation capacity perspective.
Yeah,
Does that make sense?
Yeah, I do. Kind of understand what you mean. This is more visionary stuff, right? And so if you think about a completely disaggregated storage infrastructure, those green telecom boxes in most neighborhoods, right? If that was a little data center, and then therefore wherever I went, I could bring all my content with me. It moves in a little Palmer cloud. I wouldn't need to have storage on my phone. It would just be around me. And we think that 5G networks, when they become a lot more commonplace, that will help enormously achieve some of that visionary stuff. But we're not making the raw flash, okay, which is the media of SSD. We buy it in. We buy them from 2 or 3 vendors. So it's those guys that are the ones who are driving the capacity on the phones, and they're seeing it as a feature of a phone right now, as more and more capacity. But I'm pretty sure that there's a limit to how much people will actually want to store on their phone. But what they want is to offload it quickly and reliably, but more importantly, get it back quickly and reliably when they want it. I mentioned a cat photo. You don't want to wait. If it's fallen down through tiers of storage because you haven't looked at it for 5 years, when you want it, you want it. So I think that's the challenge. It's the lag. Okay.
Right, another question?
A question from point of view of heat reuse and energy.
Yeah.
So first question is about, you show that the energies go down by the increasing the capacity, and you show the new system which also reduce the CPU and RAM. It's also reduce the energy per rack. So the question is about the how much heat is released from this one rack system in kilowatts or etc. And second question is about immersion cooling. I know that some of immersion cooling providers use helium-based hard drives.
Yeah.
And the same question for this new technology.
Yeah. So the question on the speeds and feeds, the actual heat output, I need to look up a data sheet for you. I don't know off the top of my head. I'll come back to you on that. The immersion cooling, we have got numerous projects in our server business, our storage appliance business, which are looking at new advanced technologies. Okay, immersion being one of them. Then we're working with the guys from Blocks as well. They are recycling, vegetable-based plastics and sea-borne plastics. They're being harvested and then 3D printed, immersed. People are using helium, not for the helium gas itself, but because helium is the helium drives are sealed, so the liquid can't get inside. These are all things that we're talking about, and actually we're working very much in partnership with Blocks and other partners like them doing this kind of innovation. So yeah, we are definitely doing it. And then there are new formats of storage as well that we're looking at as well, which, for example, a disk, in one of these things is pretty much spinning all the time. And when you move through the layers of data and you've got cold data, the obvious answer to that is, well, put it onto tape. But tape still has a problem with that. It requires huge power and a robot to go and get the tape you want. So, for example, are you familiar with these vending machines for drinks where the thing moves towards the thing you want and it collects it, yeah? So we're looking at, this is just an example of things how we're thinking about. We're looking at a thing where you would have the spindles in a big box, lots and lots of them, and you would present the actuator unit to the spindles that you want, and you go and get your data and then move it off. And that could be a good replacement for tape, and when it's not being used, the drive spins down. So we're looking at all kinds of things like that as well to try and drive the economy. Plus, as I mentioned on the panel, DNA storage is an exciting area where we have a lab on a chip. And we can do that. We've got them, but they're as expensive as that Ramac 4 meg thing that I showed you. It's about 28-30 grand a pop, so it's not commercial yet. But yeah, what's going on? Thanks for the question.
We are actually out of time.
Okay,
so,
thank you.
But I'm going to ask you one more question. So it's a yes/no answer. In my limited capacity as knowing much about technology, so you spoke about ghost data on end of life.
Yeah.
Is it not from my background in basic assembler and that sort of thing, you're talking about bits and bytes, and when you delete something, it just usually takes one or two of the first bits off the byte. So that's why you can't find it, so that's why it's deleted.
Yeah.
Would it not be possible to turn all those positive or negative lines into all positive or all negative, and then you wouldn't be able to find the data?
Yeah, but actually, what? Yes, I mean that's a great theory, but what actually defines it, it's simplified for presentation, is not actually the value of the actual molecule. It's the difference between that one and the one next to it, which gives it its one. Yeah. You're right. So it's hard. A good hacker can get it off. Right. So if you don't encrypt it. And so the good hacker can see the data, they just can't make any sense of it because it's so scrambled, is what encryption really is.
Excellent. I do apologise, I've run over. Okay, right.
Thank you.
Thank you. Big hand for Andrew.